A very good afternoon to all of you. So today we are going to learn about memory management functions. That is very important topic in operating system. So today we are going to discuss in memory management, basic memory management. That means what type of memory hierarchy we have, how we are managing these hierarchy, swapping, virtual memory, paging, and how we are actually establish a paging management using different algorithms like paging replacement algorithm, modeling page replacement algorithm, designing issue for paging systems, implementation issues, and segmentation. So now what is memory management? What is memory? First of all, memory. So memory management consists of two words. One is memory and second is management. Okay. So now what is memory? Memory is a linear array of byte, holds operating system and program and number of processes. Each cell is named by a unique memory address. That means every memory has their own unique memory address. Processes are defined by an address space consist of text, data and stack regions. Okay, so memory is a consist of number of byte. Process execution. CPU fetches instruction from the text region according to the value of the program counter. Each instruction may request additional operands from the data or stack. Then that data should be stored in some stack memory location, and then after that operation is going to be performed. Ideally, programmers want memory that means what type of programmer memory want. That means what type of memory which are required by the programmer, like they require large memory, fast memory and non-volatile memory. Now we have three type of memory hierarchy according to their expense, according to their speed. We have different categories like small amount of memory and fast expensive. That memory is known as a cache. Cache is a memory that lie between the CPU and the main memory. Firstly, CPU assess the cache. If there is data or pages available in the cache, then we call that as a hit. If there is page is not available in the cache, then there is signal as miss, and CPU again request for that page to the main memory. So cache is a small and fast accessible memory. Medium memory, medium price main memory. Okay, so medium and medium speed, that is a main memory. And gigabyte of memory, slow speed and cheap disk storage, that is known as a secondary storage. Okay, so these type of hierarchy is managed by the memory manager. So actually we have a fixed partition in a main memory. Like fixed partition is necessary in multi-programming, and we have classify the partition into two types. First is fixed, another is dynamic. Okay, fixed partition, firstly we discussed fixed partition with multi-programming. Multi-programming means we have number of processes in our operating system, so that processes occupy their space already partition in memory. Okay, like in this way we have 0 to 100, it's already partition, fixed partition. Only processes according to their memory processes evaluate or identify their memory, and that memory occupy according to these fixed partitions. Modeling multi-programming. CPU utilization as a function of number of processes in memory. Okay, according to the CPU processes a function in multi-programming, the degree of multi-programming is measured. So next is names and binding. Names and binding, symbolic name, logical name, physical name. Okay, symbolic name like our address like google.com is a symbolic name. Logical name, that their address or numeric value or IP addresses. Okay, these are the logical name. Physical name, actually what is the where it is lie in the main memory. Okay, that is a physical name. So symbolic name is the name of the file name, program name, printer name, user name. Logical name is like job number, minor, major devices, process ID, UIDs. Okay, physical name, that name or address actually on the disk, main memory disk. Entry point or variable addresses, PCB addresses, that means actually value or actual address in main memory, that known as a physical name. Address binding. Firstly, what is binding? Binding means linking. Okay, so we have number of bindings like address bindings, compile time binding, load time binding, execution time binding. So in these bindings we identify their physical address, like we are adding logical address with base address and evaluate the physical address. Okay, so that address can be identified in various different ways. Like address binding means fixing a physical address to the logical address of a process address space. And compile time binding means at the compilation time binding means compilation, if process location is fixed and known ahead of time. Load time binding, if program location in memory is unknown until runtime and location is fixed. That means load time binding lie between the compile and execution. Execution time binding, if processes can be moved in memory during execution. That means our process residing in the disk and can be moved into the memory during their execution. Require hardware support. So there is three type of binding we are showing. Actual program is library routine, there is an actual program and how they are varying according to their binding. Okay, compile time and load time address binding is the same. Their base address and their logical address is same, but in execution their base address is 1000. Okay, so in this compile time and execution time their base addresses may be differ. Here the base address is 1100. That base address means their actual address, starting address. Base address means starting address of the process. Dynamic relocation with the base address. Actually we are finding a physical address in memory. So there is very different way to find a physical address in main memory. Like we have physical partition, fixed partition, dynamic partition. So in dynamic partition how we are locate our physical address. So dynamic converts logical address into physical address. So memory management unit has done their work for converting logical address into physical address. Main memory management unit contain base address for running processes. Okay, so how we are calculate our physical address? We are converting our logical address into physical address. How? We are adding some base address with their logical address. That means logical address plus base address is equals to physical address. That means, and logical address is generated by the CPU and this is the base address holding by the memory management unit. Base address means their starting address. So starting address plus logical address that are generated by the CPU plus is equals to actual address of process in memory. That is a physical memory address. So there is number of protection we are using for locate a physical address. Okay, so how we are protect our physical address? using base and limit resistors. Okay, this base and limit resistors basically we are using in inverted pages. Okay, so base resistors give starting address for processor. Limit resistor limits the offset accessible from the relocation resistors. Okay, here is a logical address by the CPU. Here we have two options, limit resistor and base resistor. There we have two resistors, limit and base resistor. Base resistor consisting of base address, starting address. Okay, so limit resistor, here we are comparison our logical address with the limit resistor. Here we are comparing 0 greater than and less than limit resistor value. Okay, so here we are comparing their logical value with limit resistor value. Their value lies between 0 and limit resistor value. Okay, that means our logical value does not below the 0 and even not exceed with limit resistor value. Okay, so if logical address value is less than limit resistor value and greater than 0, if yes, then that logical address add with the base resistor and get their physical address. Okay, if their value is exceed from limit resistor and below from 0, then there is an error. So logical versus physical. Now what is logical addresses? We are talking about logical, physical, we are converting logical addresses, we are adding some base address with logical. Now what is logical and physical? The concept of a logical address space that is bound to a separate physical address space is central to proper memory management. Okay, so for proper memory management we are differentiate our logical and physical address. Okay, so logical addresses are virtual addresses and generated by the CPU. Physical addresses seen by memory unit, that means that is a main memory address. Logical and physical addresses are the same in compile and loading time binding schemes. Okay, we have already seen in presentation that logical and physical addresses same, but physical and logical address differ in execution time. So here is the features of memory management. Reallocation. Reallocation, we have two type of reallocation of memory, static and dynamic. Static means we have already fixed the memory partition, memory location before they are running. Dynamic means we have allocate their memory and reallocation of the variables and processes on the execution time. So next is protection. Whenever we are shifting a page from one memory to another, we have number of bits for protection, like it's a valid or invalid bit. So these type of protection we have available in memory management. Sharing, we can share a single page with number of processes. Logical organizations, physical organization in the main memory, and memory compaction. Memory compaction is used whenever we have a limited memory. Okay, so there is various method used by operating system for managing our memory. We have swapping, virtual memory, paging and segmentation. Swapping means actually exchanging memory location with each other. Like in this way, memory allocation changes as process come into memory, leave memory. Scheduled regions are unused memory. Okay, these scheduled regions are the unused memory. Like we have already fixed partition and we have already placed operating system in first partition, and second, if as the number of processes come into the memory, they allocate their occupy their space according to their process. Okay, so like A entered and occupy their space, B entered, occupy their space, C entered, occupy space. Okay, so in that case, if suppose D entered and this space is not enough for D, then what will do by D? So that D will replaced with a process that come first in main memory. So in that case we have a space available in A. Okay, so A is the first process that will come in memory first. Okay, so we are replacing A with D. D means D, B, C. If another, if in the another time, that means A next process will going to demand a page. There is no page is not available in our memory because it going to swap with D. Okay, so second page is B. Okay, so that means our first page we are going to consider B is a first page because A is already swapped. So next is B. So we are going to shift or swap the B with A. So this is swapping, means we have different methods for swapping, like we have number of algorithms. According to that we are swap, like first page, first out, least recently used page can be swapped. So there is a number of procedures and algorithm we are using for swapping. So actually swapping means exchanging their memory space. So like in this way, allocating space for growing data segments, allocating space for growing stack and data segments. As the process is going to increase their memory space and it will occupy more and more space in actual use. Okay. So memory management with the bitmap. Okay. So in according to our map, we have already managed our memory with bitmap. Okay, so here we have a number of bytes 1 1 1 1 1 0 0. So where it is 0 0 0, that space is going to be unused and shaded regions. Okay, means there is no value in this shaded region, that means their value will be 0 0. Okay, so in another way to represent the 0 0 value, 0 0 bits, we are representing H. H means whole. Whole means in this area we have 0 value. So how we can plot that bits in our main memory, like P is a process, 0 is the starting and 5 is the number of processes. Okay, so in this way we have representing H for whole as, and middle region is to show the starting, and the third part is showing the length of the actual bit. Okay, so next part going to point the next bit. So memory management with linked list. Linked list actually means linking. There is number of nodes and one node point to the another node by linking with each other. Okay, how they are going to link? First node will have the address of second node. Okay, 4 neighboring combination for the termination process X. For managing memory with linked list, we have number of searching process, like we have searching the list for space for a new process. So we have a number of these algorithms: first fit, next fit, best fit, worst fit, quick fit. So these are the algorithm we are going to use. So according to these methods, we are replacing or searching a new space for a new process. First fit, we are just going to occupy a space firstly. That means our memory manager start searching for free space from the beginning. Okay, and if there is any space available in the beginning side, then that process is occupied within that memory space. Either that space is more than their availability. Okay, so like we have first space is 100 kilobyte and first process take over that space 100 kilobyte, but their process only require 50 kilobyte. That space come after this space, but in first fit that space going to be occupied. Okay, this algorithm is faster, but there is number of wastage of memory. Next fit starting from current location in the list. Okay, next fit means if we have 5 processes already in a memory, then our pointer going to point the next fifth position, not from the beginning. It starts from the last occupied space, then next available free space are going to allocate to a new process. Best fit, find the smallest hole that will work. Okay, best fit algorithm used, this method is best and it takes time, but it's the best. There is no wastage of memory. How? Because like we have a 50 kilobyte process require 6 kilobyte space. It will search equal or more than space if it start from beginning to the end. If there is any space available 50 kilobyte equal or greater than or smallest, then that process occupy or allocated that memory space. Worst fit, find the largest hole, remainder will be big. Cube fit, keep separate list for common size. Virtual memory or logical memory. Virtual memory, separation of logical memory from physical memory. That means virtual memory is totally different from the physical memory. Only part of the program needs to be in memory for execution. Logical address space can be much larger than physical address space. Need to allow pages to be swapped in and swapped out. Virtual memories can be implemented by paging and segmentation, and virtual memory is generated by CPU. So this memory is implemented via paging and segmentation, because as CPU request or demand for a page, these two methods we are going to use for swap in and swap out the page into the main memory. In virtual memory, here is a CPU and here is memory and disk controller. CPU sends virtual address to the main memory unit. Okay, as the process is going to compile logical addresses generated by the CPU, and that logical address or virtual address is going to send to the main memory unit. Okay, and then main memory unit sends physical address to the memory. That means logical address is generated here, that logical address going to main memory unit, that main memory unit trace their trace their physical address in actual main memory. Okay, now how we are locating that physical address we have discussed later. Okay, so these virtual memory page is going to be implemented by paging. So firstly we discuss paging. Now what is paging? The relation between virtual addresses and physical memory addresses given by page table. Okay, so here we are number of bits. That logical address is developed by CPU, and CPU logical address consists of number of bits. One is for page, another is for logical address or offset. One is for page, another is offset. So in this way we have 4 bits for page table or index. We are going to discuss consider it as a index, and the rest of the bits is known as a offset. Okay, so these bits going in page table as a index, like we have 0 0 1 0, that means there is a 2, so it going to point 2 in page table. So 2 is considered as a index for page table. Okay, here we are getting a frame, here is a frame, here is a frame, and these are the number of protection bits. Protection bit absent or present, that page is if there is page is available in main memory, then that bit is 1. If that page is missing, then it will be modified by 0. Okay, so 2 is an index, here is a frame number, and here is a protection bit or present or absent bit. So here we are getting a frame 1 and 0. So frame plus offset bit, these are the offset bits is going to plus in frame, and these addition of these bits going to trace a physical address. So these bits generate the outgoing physical address and incoming virtual address. So in this way we are tracing a physical address using logical address. Again we are again I am going to repeat, logical address is generated by CPU address, logical address. Logical address is further divided into 2, page index or offset. Page index is going to find frame in a page table, then that frame is going to plus or add with their offset, and that offset combine with frame that generate the physical address. So here is a page table, we have number of 2 bits, first page table 1, page table 2 offset. So page table 1, it's a process ID for further insecurity or making a table fastly page access, we have process ID, page number and offset. So in this way we are tracking a physical address by adding some more bit or more bits for accessing a single page easily. So here is a 2 page table 1, 2 and their offset. So while we are transferring a page from one memory to another, we have applied some additional bits that show the status of a page. Okay, so if a page is going to modify, then that bit is going to 1. If that page is not modified by any process, then their status will show in different way. So we have number of entries like caching disable, modified if any process is going to modify a page, referenced if there is any reference with another page table, protection bit, protection means that page is valid or not valid, present or absent, that means that page is present in cache or not, page frame number. Page frame number actually used to trace a physical address. So this is translation look ahead buffer. So translation look ahead buffer is used to speed up our paging concept. So previously we have discussed simple paging. Simple paging takes a lot of time to search a single page. So translation look ahead buffer is used to make a page easily available or to speed up a page. Like we have number of virtual page, valid bit, whether a page is valid or invalid, then there is a modified bit and their protection, read write mode, read only mode, read write mode. Okay, so read, while we are replacing our page according to their priority, read only page replaced firstly. Okay, so read write page it's 1 and read only page going to 0. So while we are replacing or swapping our page, 0 will going to replaced with new process or new page. So next is a inverted page table. So there is some speed problem with previous page tables. So we have inverted page table. Inverted page table has additional bits. There is a process ID. We are adding some easily traceable IDs, process ID, then page number, then offset. So easily we are tracing our page from the main memory. So how we are replacing their pages in main memories? Okay, so there is number of algorithms. Page fault force choice, which page must be removed, make room for incoming process. That means which page is going to replaced with the new process